All right, continuing on. Talking about fuel. Let's see. Oh, I was thinking we'd take off with chemistry, but you know what? I don't think we finished talking about auto fuel.
We have the benefits.
We didn't go over the cons, so let's just clear that out. That was the professional. There we go. All right, so the cons. Well, what were the benefits again? Cheaper. No lead, so we didn't have lead fouling the spark plugs and stuff like that. All right. So what are the cons? Well, reasons why I won't run auto gas in my airplane. Well, we should say does not. Well, we say car gas. Car gas does not have the same quality control. Contains what? What does car gas contain?
Ethanol.
Ethanol. Ethanol, ETH. How do you spell ethanol? ETH.
ANOL.
Ethanol or alcohol. And other chemicals that may not be compatible with the rubbers and stuff that are put into aircraft. We already said lower quality control. Higher volatility. Oops. Higher volatility. Is that good or bad?
Both. Bad.
Well, why is it bad for us in aviation?
Vapor lock.
Yep, vapor lock. Higher vapor pressure. What does that mean?
Need more pressure to vaporize it?
Yeah, as it vaporizes, it's going to give off more pressure. That in turn can lead to more chances for vapor lock because it's actually vaporing out, and so it takes, it's creating more pressure within the fuel system, or it's allowed to. Let's see, and kind of a big one. Well, why don't I try spelling correctly? Yeah, I did. Jeez. Does not contain preservatives. Due to the high turnover. So, be interesting to see how many times a gas truck actually goes to a gas station per day. It was like last summer I had to fill up like everything. So, went to Costco in the morning, there was a gas truck. Went a few hours later, there was a different gas truck. Went later in the evening, there was a gas truck. So that was 3 times in one day I actually saw a gas truck pulling up to Costco. So it's such a high turnover, the gas doesn't need these stabilizers and stuff in it. So, but there's a lower turnover and it's, the higher quality control. So avgas stays good for a very long time. In fact, I was talking with Larry, had a barrel of it, and he said it's like 10 years later or something. He popped into it, and it's like, yeah, it's fine. Still worked. So those are all the reasons.
How long does it take to the car gas to go bad?
I don't know.
18 months, 2 years.
I was thinking, a little more than a year, but not much more. Because, I've got some that's kind of old, and the lawnmower, the kid cannot get our lawnmower started because the gas is just getting so nasty in it.
And it's just breaking down.
Yep. So one of the ways you can do it is you can stick your finger in the gas and pull it out. If your finger turns cold, it's still good. If your finger stays kind of warm, it's bad. So why does it get cold?
Evaporation.
It's evaporating, yeah. It takes heat to evaporate, so your finger should get cold. What do you do if you don't want your finger to get cold? Don't stick in the gas. All right, so a little bit of chemistry here. A little bit. Fuel is a hydrocarbon. Which means it has hydrogen and carbon. Yeah, we can skip that. All right. Does it need to be in a liquid or gaseous state to burn? Vapor. There we go. So gas needs to be a gas, right? So it. That's where they get the name. Needs to be in a vapor state. All right, what else? So what does fuel need to burn? Yeah, say it. Yep. All right, so what is the air that's surrounding us? What is it made out of?
Nitrogen.
Mostly nitrogen. Air is by weight. All right, what's it made out of? Nitrogen. What, describe nitrogen. What does that mean for us?
It's inert.
A nerd gas. Nerd gas. Inert, yeah, an inert gas. So it doesn't really, it doesn't have anything to do with the combustion process per se, but what does it provide for us?
Cooling.
Okay, cooling. What's happening when we do have combustion in the cylinder? What's the nitrogen doing?
Expanding.
It heats up and it expands, so it helps with the power. But that's not what we're too concerned with right now. So nitrogen is 75.3%. This is by weight, by the way. And then oxygen, oops, doing that over here. Oxygen is 23.15.
I guess it also depends where you were at. If you were in Beijing or wherever.
Oh yeah, well, the air is really bad. Yeah, 1%.
When the fire here.
And if we looked at it by volume, it would be 78, 21, and 1. Oops, this over here. .55%. 78, 21, and 1. There we go. So by volume. So it's a little bit different by weight than it is by volume. Which can be kind of an interesting point when we start talking about mixtures of fuels and stuff. We need to be more conscious of the weight because that's really how fuel is done. So we start thinking about this. We think about different mixtures. So here we've talked about the fuel and we've talked about what the air is comprised of. So we're worried about, or what we need is this oxygen out of the air, not so much that, not the oxygen the other, but we need the oxygen. So we have to mix the proper amount of oxygen with the proper amount of fuel to get the proper combustion and the most power that we can out of the fuel. And I mentioned yesterday this word, stoichiometric, S-T-O-I-C-H-I-O. Some people say stoichiometric, which is proper, and some say stoichiometric, S-T-O-I-C-H-I-O metric. And what that means is a chemically correct blend of oxygen and fuel. So if you looked at it from a chemist standpoint and you were mixing it up in I guess in theory or on paper, you would look at it and say, okay, I need this many oxygen molecules, I need exactly this many fuel molecules, and I'd call that, and it had a complete and total burn. There was no extra oxygen. There was no extra fuel. It's perfect. That would be stoichiometric. So let's say all the fuel is burned. Yikes. All the fuel is burned. And a stoichiometric has neither an excess fuel or air. Chemically perfect. And the proper ratio is 15 to 1. And if I divide that out, you can also call it 0.067. I like to say 15 to 1. I can picture that a little easier than I can picture 0.067. All right, 15 what to what? Well, it's a good thing, too. So that is 15 pounds of air to 1 pound of gas. We could extrapolate that out. We could say that's about 1 pound of... Nope, I don't want to do that. Let's keep it simple. There we go. But I will say, let's see. 15 pounds of air to 1 pound of gas, or 0.67 pounds of gas to 1 pound of air. Or 1 pound of air is about 13 cubic feet, or 6.7 pounds of gas to 100 pounds of air. Or we could look at it another way. We can say that's a little over 1 gallon of gas to, let me see, 1 gallon of gas to 100 gallons of air. Now, how come I can just go, now it's like 1 to 100, right? No, it's not, because what am I after in the air?
The weight.
What's in the air that I need?
Oxygen.
Oxygen. So it's only, how much, what percent of that is oxygen of the 100 gallons of air?
23.15.
Yeah. So when I say 1 to 100, it's not, I didn't suddenly change the ratio. It's 1 gallon of gas to 100 gallons of air, but I need the oxygen out of it, so it brings the ratio right back to where it used to be. But now we're talking about, well, how much does the aircraft engine actually ingest, because it's not filtering out the oxygen, right? It's taking in all of the air. So it needs 100, so every time you burn a gallon of gas, you burned 1 gallon of gas, you burned 100 gallons of air. Let's see, so that would be, I figured this out, 1,239 cubic feet, or a room 10 by 10 by, that didn't sound right, that sounds too low. Yeah, somebody wrote that. All right, so we have something called a rich mixture and a lean mixture. I'm going to pop it over to here and do something right here. All right, so we have, we'll say rich. That would be helpful if that actually worked. Nice. Okay. Yay. Rich and lean. So if we look at kind of a line between these two, there's a point at which it gets so rich, there's so much fuel and so little air that it won't run, an engine won't run anymore. And then we can go the other way where there's so much air and so little fuel that it won't work anymore. So really it goes about 8 to 1 to 18 to 1 is where our range is going to be. So we can see that 15 is going to be offset a little bit. So 15 to 1, what do we call 15 to 1? Stoichiometric. And that's 8 parts of what? 8 parts air to 1 part fuel. All right, so 18 parts air to 1 part fuel. Well, can we just run the engine anywhere in between there without any problems or just, hey, whatever? I mean, because we could, where would you want to run it?
15 to 1.
Why?
That would be perfect.
Oh, I wouldn't. If I could run it anywhere and get the same results, I'd run it all the way over to 18 to 1. Why would I want to do that? Less fuel. It's cheaper. All right. So a rich mixture that is as little as 8 parts air to 1 part gas. By weight, if I want to be specific. Expressed as 8 to 1 or with the ratio 0.125.
I got a quick question.
Yeah.
So on the backing up a little bit, it says 15 pounds of air for 1 pound of gas, 1 gallon, and then 100 gallons. So 1 gallon is 6 pounds, which would be 90. I'm a little confused on how they equal up each other.
With the 15 pounds of air to 1 pound of gas,
Yeah.
I'm almost starting to question that this is correct right here. So let me just double check that stuff. It's just almost kind of extraneous information that doesn't really matter.
Okay.
But what we're talking about down here, that matters. So a rich mixture burns slower than a correct mixture. So when we start talking about these mixtures, not only is it going to have an effect on the power that's produced, but the time that the fuel in the cylinder is actually burning. And so that starts doing a whole bunch of really weird things. And we'll talk about that in a minute. And then we have a lean mixture. That is 18 to 1 or 0.055. All right, so I did say a rich mixture burns slower than a correct mixture. I tried to choose my words on this one, in the right way. There I didn't choose them. Okay, so a lean mixture burns very slow. There's a Q&A question. It's excessive lean mixtures can burn so slow that the fuel is still burning when the intake valve opens. I don't remember the exact Q&A. Does anybody recognize that one?
That implies that the compression gases are getting The exhaust gas are getting back into the heat. They still feel
There's a Q&A question. I don't remember what it is, and it has to do. Honestly, it has to do with radials, and the answer is this. And I'll show you some charts. But what happens is, oh, I have a chart. Let's just go to picture. Here we go. All right. So here we have the best power mixture. What do you think that is? You would think it is, but it's actually not. It's probably going to be more like 12 to 1. All right, so here we have lean over here, and lean is what?
18 to 1.
18 to 1, and rich is 8 to 1. All right, so this is the time right here. So if we look at the time span, so at the correct mixture, it's going to, it's kind of right in the middle. This is the time, and it goes. I would look at this one going both ways. So even though this is a flame propagation rate, it's still a rate, which is time. So a rich mixture is going to start slowing down, slowing down, slowing down. And at this point right here, the engine dies. All right? It can't sustain it anymore. But when you go to the lean side, if you were to look at it going straight across, this is about the equivalent spot in time, right? It can still keep going. It can get getting slower and slower and slower and slower and slower and slower. So a lean mixture can burn significantly slower. And the engine is still running. You follow me on that one? All right, so one of the Q&A questions talks about backfire. And a backfire, remember, after fire goes out the exhaust, and a backfire goes through the carburetor and can blow out the air filter. Right? So a backfire is actually going backwards through the induction system. And the Q&A talks about that. And what they're looking for you to understand is that a lean burn can burn so slow, this is what they're trying to get you to think, that it's still burning in the combustion chamber when the intake valve opens. And so because of that, the flame can actually work its way backwards to the intake valve and light everything off inside the induction system. Now there's controversy whether that can actually happen, but you guys will actually be messing around with your carburetors on the ground power unit, and you'll get backfires. You get quite a few of them. Get some after fires, some backfires. So you'll see that it does happen though. All right, so back to that one. So lean mixture burns a lot slower. And then I just wrote on my notes for some reason, Q&A, excessive lean mixtures can cause burn so slow that the fuel is burning when the intake valve opens, because that's the explanation to one of their questions. This causes the fuel air mix and the induction to burn. It causes a backfire. And I wrote my things not likely, but known to happen on radials. All right. Burn speeds, which is what we just talked about. Both rich and lean mixtures burn slower than best power. But which one has the ability to burn the slowest?
Lean.
Okay. But lean has the ability to burn the slowest. So what if I go just a little bit richer or a little bit leaner? What's the difference in speeds there? A little bit richer, a little bit leaner. It's the same. Yeah, just a little bit richer is the same as just a little bit leaner. But we know that max lean can burn a lot slower than the maximum rich. All right. And why is burn speed even important?
Efficient feed.
It does. It has to do with efficiency. And then we're going to talk about some temperatures and what things are happening. But I want you to try and, kind of hang on to this thought that, well, why would that happen? If I go lean, why does this start happening? If I go rich, why does that start happening to the engine? Well, and the answer comes in the fact that you're adjusting the timing of the burn. So you want the maximum pressure of this burn to happen at what point in the engine cycle? So we have 4 strokes. We can narrow it down to the stroke. Okay, power's correct. So we want the max to happen on power. Where on power? Do you want it right at the top dead center, a little bit after, near the bottom?
Like a couple of degrees after top dead.
Yeah, because you want the crankshaft to have already started to come back around. If it happens right on the top, then you're forcing the crankshaft down. You don't want that. You want the throw to be off center so that the piston is really starting to push down on that and bring it back around. And then, of course, that the burn rate has to do too with valve timing. When you want the exhaust valve open, when you want the intake valve open, because you want the exhaust valve open after pretty much the you've used up all of the energy, right? We talked about that. If you've used all the energy that's happening with the fuel, and this isn't quite accurate, but I use the analogy, now that the expanding gas is really just chasing the piston and not doing any work against the piston, by leaving that gas in there, what are you doing to the engine?
Maintaining that heat inside the cylinder.
Exactly. You're just maintaining the heat inside the cylinder. Getting rid of it. So how do you get rid of it?
Open the valve.
Open the valve. So it's all about the timing. Well, what if you open the valve too soon? And the gas is still expanding and doing work.
Well, and you're losing actually.
Then you're losing it out the exhaust. And you can also have all the, you have hot gas going out the exhaust. Because remember, in physics, you have this hot expanding gas, but if you use that hot expanding gas to do work, what are you doing with the temperature?
You're robbing away
What's that?
you're robbing away the temperature if you're using it for power.
You are, yeah. So if you can use this expanding gas for power, you're doing work with it, then it decreases the temperature of the gas. If you don't do work with it, then you're dumping it out the exhaust. That means your exhaust gases go up. So there's this whole correlation that's going to play in between this stuff. That's it. So we got all that. Let's see. Let's make this point over here. It's way out here.
Kevin,
Yeah.
are you going to explain a little bit more about leaning procedures?
Yep. A whole bunch more. Byproduct of combustion is, what is a byproduct of combustion I don't want? I'm thinking something that'll kill you. But heat would kill you. Carbon. What's worse, carbon monoxide or carbon dioxide? Carbon dioxide will help put out a fire. So I guess that's good stuff. I suppose carbon monoxide would too. But carbon monoxide, when it gets into your blood, I don't have the numbers, but it doesn't go away. It stays and accumulates. And the only way you can really get rid of it is through time. Or if you have carbon monoxide poisoning, you may know what the treatment is for that.
Transfusion?
Hyperbaric chambers. Is anybody here claustrophobic? A hyperbaric chamber is a method to find out if you're claustrophobic. They put you in a little tube that's about that big around, and it's glass about that thick, and they seal it from the outsides, and they put oxygen under pressure.
That's what happens when you have the bends too. Scuba diving.
Yeah, but they can put bigger chambers. The ones they have at Mercy, I've seen them at Mercy. I've taken. I'm like, I'd die before I get in that thing. Carbon monoxide, which is CO. So that is a byproduct. I bring that up and I just throw this in here. It is colorless. And odorless. D-O-R-L-E. And odorless. The way, and we'll talk about exhaust systems and stuff later, but where you get heat from aircraft, piston engine aircraft, is from around the exhaust system. So if the exhaust system has a hole in it, it's going to leak carbon monoxide into either the cabin heat system or the carburetor heat system. In the carburetor heat system, it's not going to kill anybody probably, but when it gets into the cabin, you don't know that that's what's happening, and then you just kind of go to sleep. Well, for me, I get a really bad headache, and then I go to sleep. And then you don't wake up, and that does happen. And let's see, I told you guys about the FAA safety.gov website where you can go and you can watch these courses and get the award certificate. And I highly recommend it. And every year they put together something that is what the FAA feels is of massive importance. It's their message for the year. And I think that was last year's message. Anybody know what this year's message is?
Carbon monoxide?
No,
that was last.
that'll be last year's.
Oh,
This year's
running the propellers.
torquing procedures.
Mhm.
Yeah, finding out that people aren't torquing things correctly. So that's their message of the year. So, yeah. All right. So I just bring that up to tell you it's critical to inspect. It's hard to inspect exhaust systems. It really is. There's all these joints, and you got to take off this sheet metal. It's a pain in the butt. And you got to get down there, and a lot of people don't do it, and that's really causing a problem. So I'll get off the
But
soapbox.
that's a
But you gotta do it.
mandatory item for
What?
an annual, isn't it?
It's mandatory.
Yeah.
But I've seen a lot of annuals out there. It's, what's mandatory and what happens are two different things.
What is the exhaust system like made of? Like, is it just sheet metal?
Stainless steel.
Oh, stainless.
Yeah.
I believe we're on 4, Kevin.
What?
We're on 4.
We're on 4?
Yeah, we're on 4. Agree with that,
Uh-oh. Well, no, that was like mixtures. That was a subset. So we're on like all the way out to the edge, number 3 now. Sorry, because I'm not doing the edges right there. So power ratios. Oh boy. Okay. Let's see. So one was about the atmosphere. 2 was about fuel. Everything went under fuel. And then we got into, then 3 is now power ratios. Just trust me on this one before I have to go back to circles and stars and happy faces and whatnot. All right.
You'd probably be better off.
I might be. Speaking of that, not to be unkind or anything, but I decided that if you don't do well on the test, rather than making you feel bad and saying something, I'm just going to staple the McDonald's application to your test. Would that be mean or what? I would do like that. It'd be funny if you didn't get one. So, all right, power ratios. There's got to be an abbreviation for stoichiometric. Stoic. S-T-O-I-C. What does that mean? Does not necessarily produce the highest power. All right, so now that we know that. So if we could somehow get a carburetor and the carburetor actually had a printout of a digital readout of the exact mixture that we have, and by the way, I do think there is a device that does that now, we wouldn't want to dial in 15 to 1 and say that's got to be the best because it's stoichiometric. It doesn't work that way. And the reason why this is due to imperfect, I will abbreviate fuel-air mixture. Right, so we have an imperfect fuel-air mixing in the cylinder. Means all the air and all the fuel isn't perfectly mixed. It's like you're making a cake and you have the whatever and the other stuff, and then you kind of mix it once and you're like, yeah, good enough, right? And this side's wet and that side's dry. Incomplete scavenging of exhaust gas. So what I mean by that is all the exhaust gas didn't get out of the cylinder. Yeah, the exhaust valve was open, but did 100% of it get out? Nope. So that's going to throw things off. And let's see, the most power is produced with a mix of about 12 to 1. Is that richer or leaner than stoichiometric?
Richer.
That's a little bit richer. 0.003. And that is richer than stoic. Stoich. All right, so best power. So here I've got a chart. I don't know what my chart's talking about. It is the same engine, 3 different times. Here's our fuel-air ratio, which they give me between points, which, let's see, 12 is 0.083. So right there is about 12 to 1. And then this way is getting richer or leaner. Lean. Sure about that? And this one is rich. All right, so this is the power curve right here. So it's showing that the best power is going to happen right here for this particular engine at 2,900 RPM. And it's going to give me 400 horsepower. For the same engine at 3,000 RPM, it's going to give between 375 and 475. The best power happens over here. So it's getting a little... Is this right down here?
No, I want to say it's the other way around.
Yeah, I should have listened, guys. All right. And then what's going to happen over here is best power is going to happen here when I get up to 3,150 RPM. So what is changing is the RPM. The RPM is changing, and in order to make that work out, I've got to change the mixture. So what is the correlation between RPM and mixture? Why is that? Why am I getting more power as I richen it up?
More fuel?
I'm giving it more fuel. But why is that more power? Just because all I did is change the RPM, same engine.
More molecules to burn?
So you have more losses of efficiency you need to make up.
Losing efficiency. You're changing your burn rate. Am I speeding it up or slowing it down? It's based off of stoichiometric. So right here, you're on this side of, you're on one side of best power. Right here, you're matching best power. And over here, so you see how it's not stoichiometric, but it's the same curve. And we said if you go on this side, you slow it down. On this side, you slow it down. So it's, I don't know, that's what it's looking to me. So you're slowing it down a little bit, going each way. So I just want you to understand there's a correlation between that. So, you know, there's more happening than we can even really discuss and really get into great depth about. But understand that you're speeding up and slowing down the burn rate, which is going to change stuff. So it's not always just the same. You can't just take an engine and go, well, 12 to 1 is where it really should be. That's what I wrote in my notes. And as long as it's 12 to 1, everything's perfect. That's best power. Well, it's going to change a little bit depending on where you're at. So in this particular case, this happens to be the 12 to 1 spot right here. It does give me best power at 3,000 RPM. And so, you know, that's where best power is. But I've got to richen it up to get best power over here, and I got to lean it up a little bit to get over here. So that's my point. All right, so best power. That is a mixture that will give, or produce, I'll say produce, produce the maximum power. Most power. So if I'm on an airplane, I got to get from point A to point B, and I got to get there as fast as possible. I want best power because I want the most power going out of the engine to the propeller. Give me the max amount of thrust. I'm going to get the best speed, and I'm going to get there the fastest. And I just talked about that. Note this mixture is different at different power settings. In our case, we looked at RPM. Yes.
So, throttle input isn't linear at all.
No.
So when someone says they're running at half throttle, I might be running at like a quarter, really.
Okay.
So it's not linear at all.
Okay. So,
Why
in
is
fact,
it
I was thinking this would be a good
considered
time to talk about that, and you prove my point. It's a great time to talk about that. So let's start. Okay, let's start with something easy. So your piston engine aircraft, it's either going to have a fixed pitch propeller or a constant speed propeller. Fixed pitch is a lot easier to understand. Then you can move into constant speed because in constant speed propeller, you start changing your RPM and manifold pressure. In a fixed pitch, you've got one knob, just like in a car, you've got the throttle. And the throttle's just going to adjust your RPM. Manifold's going to follow where it wants to go. But like in Juan's airplane, you know, he can go it up to a certain altitude and he can say, okay, I want to change my RPM, so he'll pull back or move the blue knob, which will change the pitch of the propeller, which will adjust his RPM. Then you'll take his throttle and move the throttle back and forth, which because the RPM is being held by the propeller, when you change the throttle, then the manifold pressure is just going to go up or down. So it really becomes complicated. So we'll just kind of stick with something simple right now and just say a fixed pitch propeller. So a fixed pitch propeller, the only thing I can do is push it in, pull it back. If I push it in, the engine should go faster. If I pull it back, the engine should go slower. I'm moving the throttle plate inside the carburetor. So what, as a pilot, we have to be thinking about our power settings. And you don't take off in an air-cooled engine, an aircraft engine, and put it all the way to the firewall, all the way forward, and take off, and then get up to altitude, level off, and just leave it there and go. Right? That's too much. You want to bring it back to about a good cruise speed is about 75% RPM. So you can use 100% RPM for takeoff, but then once you're cruising, you come back to 75% RPM. So what is 75% RPM? Well, if I said that my red line is at 2,700 RPM, what do you think 75% RPM is?
18.
Okay, so the logic would you'd think, okay, well, I'll just take the 2,700, multiply it times 0.75 and get a percent RPM, right? Okay, but that's not the case at all. You're not looking for 75% of maximum RPM, which is, I think, what your point was. It's not linear like that. So you actually have to look at a schedule in your pilot operating handbook that will clearly tell you, for this altitude, this RPM is 75% power. So like for my airplane, once I get over 5,000 feet, I'm running near, it's like close to 8,000, I think it's around 8,000 feet. At 100% RPM, I'm at 75% power. Because I'm losing air. So if I'm losing air, I need to drop the fuel down to match. So I'm not getting as much horsepower out of my engine as I go up in altitude. So as I lose horsepower simply by going up in altitude, that's dropping that percent back. So the pilot operating handbook is literally telling me, run it at red line. Shoot, it's only, that's 75% or less right there. You're fine. It's just all about percent power. It's not about percent RPM.
So throttle's indirect.
indirect to horsepower.
2 horsepower. Yeah.
It really is. But it's the only thing I have to control.
So
And I have to look at
if a pilot, for example, comes and says that they were giving a half throttle, that's not even.
doesn't mean anything to
Doesn't
me.
mean anything.
It does not. Well, it means nothing to me for a couple reasons. One, like you said, are they talking about pushing the black knob in and out and measured it and said, okay, I have 6 inches and I pushed it in 3? Yeah, so you're right. It's not linear that way at all, first of all. And secondly, it's like, well, what altitude were you at and everything else? Yes?
So is it causing more wear on the engine running it at a higher RPM, at a higher altitude, even though you're only producing the same amount of power? Because things are spinning faster?
I have to believe that it is. But at the same time, look at the relative speed of the engine. The engine is only turning 2,700 RPMs. What does your car turn at? Not.
4,000.
Yeah, where's red line on your car? Yeah, like mine is like 7 or 8, you know. And so.
Going 80 down the freeway, my car idles at 2,700 RPM.
Oh, so yeah, he's idling at 2,700. So, all right, we can take a quick break.